you can see my screen. So today I want to talk about the nonlinear continuum mechanics. Okay, so let me motivate the discussion. So in general, let's consider a cubic. Okay, if I ask you what is attractions, okay, so what does that question mean? Okay, so there's a force divided by the area. Okay, so I would say that the normal stress is equal to the normal force divided by the area. Okay, does that make sense? Now this is called the normal stress. Interestingly, it's not even a stress tensor, it's a component of the stress tensor. Okay, so what this is actually n dot sigma dot n times f and equal to nf fn divided by a. Okay, does that make sense? Okay, now but then I want to ask next questions. If I have if the material is very soft, okay, so imagine that I apply the force, but the material is very soft, like for example a rubber, okay, or actually apply a lot of force on the elastic material so that it deforms significantly. Now the material actually look like this. Okay, it gets squeezed so hard that it becomes much fatter. Okay, so this is actually apply some deformation to it. Okay, now then I have a new problem here because I have original A. I would denote it as the original A, right? And now I have the new area. Okay, in this case, the new area divided by the original area is actually much greater than 1 in this particular case. So now then if I want to define tractions or actually the normal stress, so which normal stress are we talking about? Okay, is it F divided by AO or F divided by A? Okay, so one thing that is important is that they're not equal to each other anymore, right? Does that make sense? Okay, so which one should we use? Now there are different theory or different view on that, and the first thing we need to actually that separate the small deformations continuum mechanics and the finite strength continuum mechanics is the distinctions for different configurations. Okay, so if I want to actually define the stress in the current area, I need to take account of the change. Okay, does that make sense? So that I can actually define the stress in a proper way. Original example we did here. Okay, you can actually see that I don't really need to distinguish A and AO that much if A divided by AO is actually pretty much close to 1. Okay, but what if the is actually A is actually 1,000 times of A? Okay, so what will happen to when you compute the tractions? It would be 1,000 times different, right? By actually you consider the deformations. Okay, so this thing is actually the nonlinear continuum mechanics is necessary when the material is very soft, or actually when you apply a very large force to it. So for example, if you actually want to model the plastic surgery or actually anything to do with the with a soft tissue or actually food processing in a finite element or whatever that deal with very soft material, then the large deformation continuum mechanic is necessary. Okay, but for rock mechanics, for things that are very brittle, very hard, they are actually less. Okay, so let's take a 10 minutes break and I will come back. Okay, let me continue. Okay, So this is the motivations, and then what we actually need to consider is that in general, I have a body, and I would assume that it's simply connected, meaning that if I have a one point and another point, I can actually find a way to connecting them without any issues. Okay. Now I'm going to apply the deformations, and then in this case, if I have a point x, all the point in the collections of, so if this body B is consistent of a collection of point x, then each x could be applied with a mapping with the original x, taking the x and t as an input and apply to a deformed configurations. Okay, so I apply the entire deformations mapping into the body B, and then I get a new shape. Okay, does that make sense? Okay, so this is called deformation mapping. And in general, I'm going to assuming that the inverse of the mapping also exists. So the inverse would take the current x and then the t and then map it back into the original x. Okay? So under what case would the inverse mapping exist? One example it won't exist is that if originally I have 2 points x1 and x2 and then we map into the same x, then can I define the inverse? I cannot, right? Why is that? Well, because if I apply the whole loop, I actually may not get back the original point, right? You see what I mean? Okay, so they're not one-to-one, okay? Now, this mapping exists, requires certain property. One important property is a one-to-one mapping. Meaning that if I have a point x and I can map it into from the reference configurations, I can map it to the current configurations with a distinguishable point. Okay, so here the word distinguishable is different, is important because it means that if I have a distance here, okay, so if I have a 2 point that have a finite distance, in here, that distance is going to be finite. It could be much larger, it could be much smaller, but it won't collapse into zero. Okay? Does that make sense? Now, why do we need that? Okay, because we are thinking about rewriting the kinematic and the kinetic while taking account of the fact that the current configuration and the reference configuration are different. Okay, meaning that I want to make sure that I separate the descriptions, or I keep track of, I take account of the effect of the geometrical nonlinearity or the change of the configurations. Okay. Now with that, then I would actually define something. So can you guys see that the mapping from the reference to the current configuration is some kind of motions? Okay, given the time. Okay, it's a mapping. So let's say I describe, let me give an example. If I write in a 2D, okay, I write x1, x2 equals to ax1 plus b equals to ax2 plus c. So, okay, how does it look like? Okay, and then these x1 and x2 are actually on a straight line here. Okay, you see what I mean? Oh, and x1 and x2 are coordinate. So how would that mapping look like? So I haven't defined what is ax1 and plus b and ax2 plus c, but a, b, and c are actually all just a scalar. Okay, so how would they look like? So let's give an example. So if the original x is actually if originally I have a point x1 x2 equal to 0 0. So what is the new deformation? What is the new point? Okay, let's say this one is actually 0 0. Okay, what will be the new point x1 and x2? It will map to where? B and C, right? Okay, let's put another point. If the original thing is 1 1, so what would that new point map you to? Let's say this point is 1 1. What will be the new point? It will be A plus B and A plus C, right? Okay. So what happened to anything in between these 2 points? It will be a straight line. Why is that a straight line? It's a linear mapping. Okay, excellent. Okay, so you get it. So the mapping is simply, now is the inverse exists? Why is it exists? Well, I can just back substitute, right? Well, what would that look like? Well, what would that look like? I would need to write x1, x2, now in terms of x1 and x2, right? More accurately, more generally, it would be something like this. Okay, but in that case, in this particular case, I won't have that. But what would that be? Okay, very good. Okay, so this is actually the mapping. Okay. So now let me ask you another questions. So how do I define the strength if I want to know the strength? What is the right way to find the strength? Okay, so or another way, I have that deformation mapping, right? What is the deformation gradient? What is the gradient of that deformations? Can anyone see that? Yeah, F deformation gradient is actually equals to A00A. Okay, why is that? So this give me some kind of strength, okay? Some kind of strength measure. Why is that? It's just a derivative, right? So in fact, that may be easier. This is the linear mapping. If I write it, or if I rewriting it, I have A00A x1, x2 plus BC, right? If I want to write matrix one, this is another way to write it, right? Okay. Why is the deformation gradient doesn't have the term B and C here? It's a rigid body motion because all the points are subject to that B and C movement first before I actually have a relative distance that is defined by that A, right? Okay, so if I have 2 points in the reference configurations and then I move to the new 2 points in the new configuration, imagine that that pair of points is moving from New York to New Jersey, okay, or whatever. But then the distance between the two haven't changed, right? So that would be just a rigid body motion, right? Okay, it shouldn't cause any strain, okay? You see what I mean? It's the relative distance that getting changed for 2 arbitrary points that register into the deformation gradient, okay? So Okay, so this gives you an example. Now I will motivate for another example. So if I have that mapping, what is the velocity here? Okay, that would be 0. Why is that? Yeah, it doesn't depend on time, right? Okay, so I don't know what is that. But what if I write t here? Okay, what is the velocity? Yeah, okay. Velocity would be b and c, but how is that velocity defined? Is it defined in the current configuration change or the reference configuration change? Huh? But reference doesn't change. You have the same reference, right? Okay, so in fact, let me work on it in details. Okay, so I have that mapping. Okay, and I can actually define the deformations mapping as this. Okay, so this is actually the vector x, this is the vector x, and this is time, is a space-time mapping that give you the deformations. Now, when I consider the velocity, okay, viewing it from the reference point of view, that means that I have this potato in the x configurations, and then from this, I want to actually see what happened in the x. Okay, and I express the velocity in the current reference configurations. So what it actually translates to is that I try to compute the change of the time of that mapping with respect to x and t, right? Does that make sense? Okay, so this is actually the mapping. I use the mapping to describe that things are changing. Okay, and this would give me the velocity. Okay, this is actually easy to understand. And that velocity could also be re-expressed if the inverse exceeds as the current from configurations x at a point in the current configurations like this, right? Okay, does that make sense? If I want to describe the original, if I actually want to describe a mapping, okay? But what is the difference between the two? In this previous case, V is actually defined with the bases that are spanned by the reference configurations in the reference configuration x1, x2, and x3. Okay, so I will use the capital letter I to represent 1, 2, and 3 directions. Here, I actually need to perform the inverse, mapping it back into the reference before I try to define the same velocity. Okay, so in this case, I would actually have the velocity defined, but then it would be in the current configurations. But notice that this is actually inside this inverse mapping. Okay, you see what I mean? And then the same thing for the accelerations. If I want to define accelerations in the reference configurations, it would be actually the partial derivative of velocity in the reference configurations, and it would also equal to the second derivative, which is actually the okay, does that make sense? Okay, now, but then there is one thing that actually interesting. If I look at the acceleration in the current configurations, okay, so notice that x itself is also a function of the mapping, right? Okay, you see what I mean? Because this, can you see that? So first, this is actually the deformation mapping. that actually map from the reference to the current configurations, okay? Like a transport pan to map into the current configurations. And now accelerations itself is a function of both these current configuration x and the t, okay? If I want to expressing it in the current configurations, okay? So if you have two variables and you want to take the derivative of that variable, so what will happen? If A is a function of x and t, then if I want to actually take the derivatives, then what would happen? I will have to use the chain rule, right? So let's see that from the point of the velocity point of view. That defined like that, okay? And now I actually want to define the acceleration, which is actually a derivative. I would use the total, this to refer to total derivative of vxt. Then what would actually happen is that I would actually need to compute the current velocity with a fixed, with the deformations configuration fixed. And then that would also equals to when I actually consider the x t corresponding to the spatial derivative x plus this times the partial velocity times the time partial derivative of deformation mapping with respect to the time. Okay, so basically the first thing I fix is x, the second term I fix is actually the t, right? Does that make sense?
So the bottom, the denominator should be an x for the second.
Yeah, sorry. It should be x. Yeah, you're right. Yeah, or maybe something like this. Or actually, let me put it in x so that you won't confuse. Or maybe better yet, let me take this thing out. Oh, I don't know what happened. Okay. Now, what is a partial derivative with respect to x? Now, v is a vector. X is also a vector. Okay. So if I actually want to, and acceleration is also a vector. So if I have, and this is simply the velocity. So if I actually want to obtain another vector, so what would be the rank of this physical quality? It would has to be a second order tensor, right? Okay, so in fact, this is actually the gradient of the velocity. So I would simply write this plus, this is actually equal to the velocity, so I write v dot gradient of velocity. Okay, and this is actually also called convection term in the literature. And if you take the next semester's class on pole mechanics, you will see a lot of convection term here. And now in terms of notations, d divided by dt is called material derivative or material time derivative. And this is actually equal to the spatial time derivative plus the convection term. So we often write something like this. Okay, so far so good. So this gives you the kinematic of the displacement. So displacement is special case of the deformation mapping when you consider a linear, the distance between the two linearizing distance. And from that, we can actually start to measure, to build other other measurements. One is actually very important for large deformation is the deformation mapping. Sorry, the deformation gradient. Okay, the word gradient is actually imply what? What is the meaning of a gradient? So imagine that you have a scalar functions, okay, that actually have some geometrical shape. What is a gradient? The gradient is simply the basis for the tangent of the linear space. Okay, does that make sense? Okay, what is divergence? Divergence is the chase of it, okay, or actually just summing up those components together. Okay, so a deformation gradient tell you what happened in a particular point of the at the particular locations, what is the relative change between the distance in the neighborhood. Okay, so this is actually written like this in the tensor notations. Now, because it's actually the linear deformation, so you can also write f. Oftentimes you write Fij as a component, and J is actually in capital letter. Okay, do you know why? Because if I'm linearizing a deformation itself could be nonlinear, but if I'm linearizing it, I would always get Fx plus c. Does that make sense? Okay, let me give you an example. Okay, so let's say I just consider 2D again. 1x2, and that is actually equal to x1 squared plus x2 squared. Okay, does that make sense? What is this thing doing? Can you actually see what happened to that mapping? What is the physical, what will happen? Okay, so let's say I have a cubic, and then for any given point x1 and x2 is actually the original coordinate. Okay, if the x1 x2 are the coordinate, so what would be the deformation look like? So at x equal to 0, is there any deformations? Okay, so the point actually, so at that origins, the point actually doesn't move at all, right? Okay, so what happens if the number of x1 and x2 grow? Okay, the larger the number, the more you see the difference, right? Because it's a quadratic equation, so you kind of have a nonlinear mapping. Okay, I don't really want to draw the entire cubic, but maybe in one point that would probably look like something like this. Okay, or maybe I can try so if x1 is this, then x2 was 0. So this is actually for x2 equal to 0, it will grow. So I don't know, maybe something like this. Do you think so? Probably not. Okay, let me try. Let me do some. Let me work harder. Okay, so I'm very slow, but so at the origin point is not moving, right? Okay, so how about at x1? How about at 1 1? If actually x1 and x2, the big x1, big x2 is both equals to 1, what is the mapping? Still the same. Okay, but in between what happened? So how about 1 0 and 0 1? It also doesn't move, right? This 4 point, right? Is it? Okay, in between what happened? So what happened to point 5? 0.25, right? So, right, okay, so if I actually have this point, it will be moved to here, right? Right, is it? Okay. What about the other part? Probably the same, right? Because I don't have anything depends on x1, right? So if you look at it, I will still get this. Okay, so that look like the boundary haven't changed, right? But what happened inside? Now, if you have a grid look like this, what will be the new grid? It will get pushed into here, so I will get something like this, right? You see what I mean? Does that make sense? Isn't it? Anyway, so so here I don't want to test your ability to visualize the mapping, but what instead I want to point out is that what is the deformation gradient in here? The deformation gradient is approximations of these mapping that are nonlinear, but they are linear. Okay, so if I want to approximating that, I would compute this as a function of x. So this one together give me an index of I, this give me an index of j, right? So what would I do is that I would take if I want to linearizing this mapping, what I would actually do is that I will assume that this is actually equal to f x at the current given point for the x, right? You see what I'm plus c plus some constant, and in this case that would be nothing, right? Because I don't have a residual, I don't have a constant number here, right? So what would be the deformation's gradient? In this case, what would be the deformation gradient? That would be just 2x1 and 2x2 0 0, right? Okay, does that make sense? Okay, so now if I put it in this deformation gradient on, if I actually put this linear mapping in the given point, I will actually get back the tangent. Okay, but then of course you cannot approximating that thing with a particular number, because at different point I actually have a different deformation gradient, right? Does that make sense? Okay, so here I just want to convey the idea that the deformation gradient is some kind of strength measure, but it's actually the linearized versions or the tangents of the deformations mapping. Okay. Now, how do I determine if I actually have in this case the mapping is pretty clear that I can compute the Jacobian easily, because this function doesn't contain any x1, so there is no distortion. I know it from the beginning. Okay, why is there no distortions? If I want to introduce off diagonal term here, I have to put some function of x2 here, x2, x1 here, right? So that I can distort the xy coordinate. You see what I mean? Otherwise, I'll just do the rescaling in the x1 and x2 in some nonlinear fashions. So if I write it in this way, so the first line without any x2 function there, the second line without any x1, I just do a scaling without changing the shape of the material. Okay, does that make sense? A break. If I have a material that is supposed to this, how do I actually know whether in this point it becomes bigger or it becomes smaller? How do I just tell the size without thinking about the shape? Okay, how do I do that? Let's say I actually initially have a cubic here, and then I have the deformation mapping. How do I know whether this mapping become bigger like this or become smaller? For any given point. So each point that how do I actually measure the difference? The determinant, but I guess the thing I also want to convey is that why is it deformation gradient? So J is called the Jacobian, and Jacobian is simply the determinants of f. Now this is related to our previous argument, okay? So, I define the deformation gradient as some kind of tangent, but why the determinant of f actually give you the sense of the distance, or the sense of the volume. So in the reference configurations, if I have a cubic dv, then it would be equals to dx, dy, dz. Okay. So the change in the x direction, change of the y direction times the change of z direction give you a volume, right? Now in the current directions, I will have dv, that v is not velocity here, but the volume. So I have dx, dy, and dz. How is these two things related, and why is actually the determinant? Yeah, okay. So this is actually a good way to think about it. Yes, it's related to eigenvalue. But what is the determinant? What is another way to calculate the determinant? You can calculate the determinant by actually calculate this f11, f12, blah, 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 blah. Okay, but what is the other simpler way to compute the eigenvalues? To compute the determinant. It's actually equals to the eigenvalue of f times the three eigenvalue of deformations times together, right? Okay, so why would that relate to the volume? Now, that is actually related to another concept. F, this is a deformation gradient, right? If you're actually if you perform a polar decompositions, meaning that I perform an eigenvalue decompositions, or actually something like that, something very similar, I can have a polar decompositions that's separating them into the rotation tensor and the right stretch tensor. Okay, you see what I mean? What is the eigenvalue of R of rotations? If I rotate something and then I describe it as a rotation, what is the eigenvalues? They're all one, right? If they're not one, that means I deform it. Okay, you see what I mean? The whole point of rotation is you don't touch the shape. The whole thing just change the coordinate without doing anything else, right? Okay, so this is one. So which one have an eigenvalue that are not equal to one? Just u, right? Okay, so now what actually happened is that if I actually take out the rotations, dv, the small v dv is actually equals to lambda dx in the principal direction, not the original one. Lambda 1 dx1 times lambda 2 dx2 times lambda 3 dx3, which is actually equals to lambda 1, lambda 2, lambda 3 times the dv, right? Okay, does that make sense? And this is actually just the Jacobian of dv. Okay, does that make sense? Okay, so this is actually one way. Now I do want to emphasize some difference in the large deformations, and they are actually very important. In what we talk about, how do we measure the volume change? We use the chase of the epsilon, right? Now here in the large deformation, I use the Jacobian. Okay. Now chase of epsilon and Jacobian, they're not identical. Okay, you understand what I'm saying? Okay, so which one is actually a good way to measure the distance? Which way is actually more accurate? Okay, Jacobian is actually take consideration of the nonlinear mapping, so you have the Jacobian. But what is the relationship between the chase of epsilon and Jacobian? Actually, they could be related by the lateral knot. The lateral knot of this is actually equal to the infinitesimal, the chase of the infinitesimal string. Okay, this is actually related to the logarithmic and tangential mapping that we will explain it later. Okay, you see what I mean? But here, this is the idea of Jacobian is actually, again, very important because Jacobian give you a measure of how this whole thing is changing without considering the change of the size, right? Okay, so in fact, okay, so far so good? Okay, so we take. Okay, so now I will start to build something step by step, and then ultimately at the end of the lecture you should be able to write a large deformation with time mapping, which by the way you can also using it as your course project if you like. Now there's an important formula, Nelson's formula, which is actually say the following: the current normal vector times dA is actually equals to the J times the F minus T dot N dA. Okay, can you follow? Okay, this seems very difficult, but let me explain a little bit, okay? So suppose I have a body, and then on the surface, I would actually consider a very small portion, dA, which is in the reference configurations. And then that small portion has a normal vector, just like this eye pen and my surface, there's a normal vector n. Can you all see that? Okay. Now, I want to know the relationship after I deform it. Now, this mapping becomes dA. Okay? And then I have the new vector n. Okay? Now, spoiler alert, because I have all the point x here. So in the neighborhood, there's a x. There's all the x, delta x neighbor that are on the neighborhood. I need the neighbor to give me the normal vector, right? Do you know why? In order for the normal to exist, the tangents need to exist, right? If the surface have a lot of jump but there's no tangent, I cannot really define the normal vector, isn't it? So there's an n and then there's a small neighborhood on it, and then that neighborhood, if I actually make the neighborhood very small, it will be completely flat, right? You understand what I mean? So the whole thing is non-linear, okay? But I just look at a very small portions and I'm linearizing this whole thing. And after that, I have normal vector n, right? Okay, so now, why would this thing happen? Why would I need to provide a J and F minus T? Okay, so what's going on here? Okay, first, it's actually coming from the dA. Okay, what is the relationship between this dA and this dA? Okay, how do I, if I have a current, if I have a reference area, if I actually have a reference area here, how do I know what is the new area in dA? How do they relate it? I think it's obvious that you will see F. I think you can easily see that F dA is actually equal to dA, right? Does that make sense? Okay, at least in a approximate term. Okay. So but how do we actually get this? How do we give rise to these expressions? So I want to, so this NDA is very important because in the current configurations, okay, let's say this is 2D. I want to describe what is coming in or coming out. Let's say I want to write a hydraulic model. And then the material is deformed, and then I need that NDA term to actually write my balance of linear momentum, for example, or actually tractions or actually hydraulic problems. So, but then the problem is that how do I map it back into the reference configurations carefully? Okay, so how do we do that? Okay, so now we need to think about what happened to the n vector. In fact, the easiest way to think about the n vector is to consider this as the f minus t dot nj. Okay, so this is actually well known. And the reason that we're actually coming into this expression is because we want the norm of the n and the norm of the n to be both equal to 1 in order to be qualified to the directions. Okay, during the deformations, the reference n and the current are actually, during the mapping, the material is deformed, so the normal direction is changed. So in order to map it back, I need the f minus 1. But I also don't want the f minus 1 to change the norm to be not equal to 1. So I add back so I times it by j to actually normalizing that f minus 1 so that n and n can both have the norm equal to 1. Does that make sense? So in fact, this j f minus 1 minus t could have a specific name, is some kind of isochoric deformations, meaning that the determinant of it is actually equal to 1. Okay. Now with that, then we can actually define the normal vector times the dA that it will be used a lot in defining the boundary conditions. Now there's also another thing. This is actually a little bit dry here, but equally important. It's actually the time derivative of f. Okay, so if I were mapping and then you change with time, so how do I define it? Okay, so now one thing to actually recall is that the x, the original x, is actually mapped in a space-time manner. So for different time, I will have a different x. I'll take this different small x, okay, to describe the entire deformation process. So for example, let me give an example. I think that this is actually good to come up with some equation to explain. If I start with a circle, okay, and then given enough time, it becomes more and more ellipsoidal until it eventually becomes a straight line. Okay, how would you write that deformations? How would you write that deformation mapping? There are more than one way, by the way. How will you write that? So eventually it becomes a straight line when time approaching infinite. Okay, maybe I give you more encouragement. Okay, so it won't become a straight line because time never go to infinite, but they will approach being an infinite line. So how can you write a deformation mapping? So by the way, what happened at the end? Okay, so in order to write it, you have to think about it. What is a circle? A circle is just subset of the Euclidean space where x squared plus y squared equals to some number, maybe 1. Okay, let's make it a unit circle. Okay, now I don't really need to think about that per se, because I just want to define the deformation mapping. Okay, so I already defined a subset. Okay, now I want to define the mapping so that eventually what happened? What happened to the current configurations? Huh? Yeah, y could equal to 0. Okay, you can moving it, but let's say, okay, this is a very good insight. Y equal to 0 everywhere. Okay, no matter where it is originally in x. What happened to x? Well, x gets spread out, right? Okay, originally x is actually bounded to be in minor 1 and what is this? It's actually what is the bound of it? Yes, is it? Yes, it is. Sorry, just a little bit. Have a little brain freeze. It's 1 and 1. Okay, so eventually what will happen? It will be minor infinite and infinite. Okay, so in between, how do I actually create that? How do I define the deformation mapping? Actually, computer animation is just to find the mapping. If you know how to do that, you can already make a cartoon of this, right? Okay, so what would that be? Now there's some hints for you. Okay, I draw it to this. If I look at the major principal directions, has the principal direction changed at all? Okay, so it hasn't changed. So this is already a hint. So what happened to the mapping? If I want to write x1, x2, or xy in this case, if I want to write xy as some kind of mapping of x and y, so what is the hints here? The principal directions remain identical, right? So what does that mean? There's no shear, right? Okay, so this would be a function with only x, and this would be a function of only y. Now I need to figure out what I actually need to do so that I add the time dimension there, so that when time go to infinite, then x would go to x would actually spread out, and y would also y would collapse to 0. And there are more than one answer, by the way. So why don't we try something and see whether it works? Okay, do you think so? How about this t and minus t? So what will happen? Will it work? Let's put some point there, okay? So let's put let's do a experiment, okay? Maybe that would actually help. Let's put this 1 point and 1 point. So this is actually 0, 0, 1, and this is 1, 0. Okay, so at time going to infinite, what happened to that 1, 0 point? It will approach, x will approach infinite, and y would actually remain 0, right? Isn't it? Okay, so what happened to the 0, 1 point? So 0, 1 mean x equal to 0, y equals to 1, right? Okay, so what will happen to that mapping? For that particular point, the velocity, the mapping would simply equals to what? 0, x would be 0, and y would actually be equal to 1 divided by t, right? So what is 1 divided by t when t go to infinite? 0 will be 0, okay? So what happened to this point in the current configuration? Originally is here. So what happened after time equals to infinite? It will drop to the center, right? You see what? Does that make sense? Okay, so using your imagination to think about the mapping can give you a sense. Now, I just want to using that example to talk about the time derivative of time because I want to show one very important concept. Deformation gradient, okay, in this case, time derivative of f. What is the f here? What is the f here? F is actually equals to t 1 divided by t 0 0 xy, right? Okay, does that make sense? Did I make any mistake? I don't think so. So, okay. Okay, so what is f dot? F dot is actually equals to the total time derivative of the deformation gradient, which is actually equals to the, what? Which is actually equals to the velocity, gradient, velocity derivative corresponding to the reference x. Now this can be rewritten as the velocity of the current x times the deformation gradient, times the deformation gradient itself. Okay, can you guys see this? Okay, now what happened to this? Is the following. This is something very interesting. This is called L. L is called the velocity gradient dot f. Okay, so the time derivative of f is actually equals to is also a function of f, is the velocity gradient times the deformation gradient itself. Okay, one thing that are very important is that this is actually this is called the velocity gradient, and velocity gradient is corresponding to the current configurations. Okay, now there's a long history of that velocity gradient because sometimes the constitutive law is written as a function of velocity gradient. Is it true? Actually, no. If you write it as a velocity gradient, you will actually have some problem. L is actually called velocity gradient, which is actually literally the spatial derivative, spatial gradient of the velocity. I will put a small x there to distinguish the great x, and this is called the velocity gradient. Okay. Now, what is actually funny or interesting about that dl is that you can split it into two parts. L is actually also equals to the weight of deformations and the spin tensor. Okay, what is the weight of deformation is 1/2 of the gradient velocity times the transport versions of it. Okay, so this is D, and this is called weight of deformations. In your undergraduate course on the deformations in the strength, you basically can actually easily see that this is actually just epsilon dot if I have a small deformation. Do you know why? Because epsilon by definition is 1/2 of the gradient of u plus the u dot the gradient operator, right? Okay, so you just basically I just exchange that u with v. Oh, sorry, u and v here. Now there's another even more interesting term is W. W is 1/2 of the skew symmetric part of that velocity gradient, and this is actually called the spin or vorticity if you're actually into the fluid mechanics. Okay. So do you write constitutive law using the spin? Sometimes you need to use the spin, but does the spin store the energy? Okay. What is that spin is doing? Okay, so this is a way of deformations. It literally tells you how fast the material deforming, and what is W telling you? It's actually the fact that if I hold the deformations constant, how fast it's actually change your orientations. Remember the relationship between the spin and rotation tensor? Do you remember that? Okay, spin tell you the change in the linearized in the Lie algebra of the deformations. Okay, so in the classical hypoplasticity, you would directly replacing the epsilon dot with D, and that is actually sometimes the end of it, except that you also need to write the stress in a waveform that we won't cover. Okay, but W is actually important, but you need to, in the sense that when you write the constitutive law, you don't actually want to directly use the velocity gradient, for the fact that if I actually doing that, then the spin would enter into the constitutive model, and that is not work. That is not going to work. Okay. Sorry about that. I'm actually about to get to the stress and defining everything, and once we get there, we can actually write the large deformation constitutive law. Now, there's another thing that I'm really that I would like to talk about is the polar decompositions that we already touched base a little bit. What is polar decomposition? Is that for any deformation gradient, I can always decomposing it into two terms. One is the rotations, another one is the stretch. There are two types of rotations. I can put the rotation on the left, and I put the rotation in the right. Okay, what is the physical meaning of that? Okay, they have a different physical meaning. So remember that the F is actually IJ. J is in capital because I actually the second index is applied to the reference configurations, and then the I index is actually mean to be the not to be the dummy index. So this would be the new index that left after for the base that are in the current configurations, right? You see what I mean? So what is U? U would be the stretch, okay? You see what I mean? If I actually want to write the stretch, and then let me put the IJ here, okay? So what would be the term here? Actually, maybe I'll put the K here. Then I'll have IK, right? Okay, does that make sense? Right? Versus if I actually put the J in the right directions, I will also have K, J, but then IK would be actually here. Okay, but then the important part is that the left and right stretch actually have different meaning, in the sense that let's consider this. Okay, let's consider a circle. If I actually have the right decompositions that get the right stretch, what I mean is that I'm going to, let's say, making it longer or whatever while keeping my principal directions, and then I rotate. So eventually I may get something like this. Okay, does that make sense? I will apply the U first and then the R. Okay, does that make sense? Now what happened to the left part? I will first apply the rotations, and then I will rotate it into here first. without apply any deformations, right? And then in that new orientations, I would actually apply I will apply the v. So v here is not, again, so not to confuse you, it's actually the left stretch, and that is actually not a velocity. But then I would actually making it longer. So both cases will give you the final shape. It's just that the kinematically they are actually performing the deformation and rotation in different order. Okay, does that make sense? Also, one thing that are actually important is that these two rotations could be the same. Okay, however, the u and v in general they are not equal to each other. Does that make sense? Okay, so let me write it down. And again, r dot rt equals to rt dot r equals to identity, because rt is actually equals to the inverse of r. Okay, so far so good. Okay, now I want to say that in general, you are not going to use the deformation gradient to write constitutive law. Okay, why is that? Sometimes people did it, okay? But sometimes people doesn't want to using it. The thing is that for very simple reasons, one of the obvious reason is that it make the implementation longer, because f itself is not necessarily a symmetric tensor. Okay, f could be symmetric, but f don't need to be symmetric. F need to be positive definite in order to be one-to-one, but it doesn't need to be symmetric. So if it's not symmetric, then how many components do I have in 3D? I have 9 components. So I unnecessarily make the model more complicated. Instead, what? Go back to this. Okay, this is u and then r, right? Okay, what in these two steps, what is r doing? You can argue that r did not do anything deformation wise. It's just rotating it. You just change your perspective of looking at it, right? Okay, so on the other hand, and then the deformation is already performed here. So this stretch in the principal directions. Okay, so on the other hand, what happened to this path? This second path. I rotate it first and then I stretch. So how I rotate it will affect how I stretch. Okay, imagine that you put it into machines that are going to stretch. If the shape is actually like a triangle, how I put into this thing and I stretch will give me a different shape, right? Okay, so what actually happen is that I will use a different strength measure. Okay, what is the strength measures? Basically, it's actually coming from that polar decompositions. One is called the right Cauchy-Green tensor. Or right Cauchy-Green deformations. Right Cauchy-Green deformation is simply put the ft on the right hand side and keep the and the left hand side, and f on the right hand side. It's actually called right Cauchy-Green tensor in the sense that if I do the polar decompositions, I will get this. Or sometimes I will like write u out. Okay. It's actually called right Cauchy-Green tensor because this is corresponding to the right stretch. Okay, this is actually called it right. Now, I want to write it again in the index style. So Fij is actually the two-point tensor that have one index in the reference configuration J and one index in the current configuration I. So if I write J, if I actually have the transpose of J, what would that be? So A transpose would have the index of I and sorry, maybe I should use another one. I will have an index of let's say m and I. Okay, does that make sense? Do you know why the first index is in the reference and second is in the current in the transpose? Because it's a transpose matrix, right? You understand what I mean? I will swap the order. Okay, now I is a dummy index, right? So I would actually have CMJ. Go that. Okay. What is M and J? They are both capitalized, right? Okay. So CMJ. So the right Cauchy green tensor are actually defined only in the reference configurations. Okay, you see what I mean? So none of the index using the vector, using the basis in the current spatial configurations, all the index are in the reference configurations, which is convenience if you actually already have a reference deformation defined. On the other hand, for implementation purpose. So now then it has something to do with where the R is placed. Okay, so F equals to RU. What is that R is doing? What is that R is doing? So going back to this, the left Cauchy green tensor. What is left Cauchy green deformations? It's actually I write it as B and B equal to F dot FT, which is actually equal to V dot RT, R dot RT dot V equals to V2 V square. Okay, or maybe VTV equal to V square. Sometimes people like to write that. Okay, so what is so interesting about this? I guess it's actually interesting in the sense that Bij, I won't write down the details, are all in current configurations. Okay, you understand what I mean? Does that make sense? Okay. This is actually pointed out by my one of my PhD students that take this course. He asked a very thoughtful question that I thought is really good. Can you use the Bij to actually model anything anisotropic? Can you? Okay, I think none of you seem to have the answer. Why is that?
It's not framework. It's not objective.
It's not because of that. But you're right. I mean, if you write in C, it's guaranteed to be objective, but not in B. But what is the problem in B? So I guess the right question is that why C is guaranteed to be material film difference, and why B is not. Okay, the second problem. So what happened to the B? I use the B matrix. I actually imply the material is isotropic. Okay, because I'm saying that whatever I put in there, because I want to, B is a function of left Cauchy green tensor. And left Cauchy green tensor, and this value is actually not depends on the directions where I apply the loading. It only care about the eigenvalue. So I end up actually indirectly assuming that the material is isotropic. Okay. And the same work, you can actually find more results from the Church-Style paper on hyperelasticity. Okay, so far I described the string. Okay, so what do you think about the nonlinear continuum mechanics so far? It's much more difficult, right? Okay, why is it more difficult? What is the price of being so? Why do I care about right Cauchy green tensor, left Cauchy green tensor, deformation gradient, Jacobian, all those kind of things that doesn't exist in small string. Okay, the reason I care about this is that you can actually using it to more precisely model the material that undergoing very large deformations. Okay, you can argue that if your string is 0.0001 and then the Jacobian is very close to 1, I don't really need to distinguish the reference and current configurations. Okay, so let me talk about another problem, which is actually the stress. Okay, let's go back to the motivation problem. So how many different types of stress would we need to consider? Okay, stress as a tensor, the most famous one is the Cauchy stress tensor. Cauchy stress is actually sigma, and I will give the sigma to the Cauchy stress forever, just to respect what other people are using. Okay, Cauchy stress have two current configurations. I have the index that is referred to the spatial configurations. Okay, so why is that? Because the Cauchy stress, the tractions of the corresponding Cauchy stress is actually considered by thinking about the current force in the applied on the deformed on the configurations derived by the current area. Okay, so this is a classical thinking of the stress. However, they are not always very convenient to use. And then there's another stress that are called Konikov stress. By the way, there's 2H here. It's not a typo. And they also have the current index, but that would be the Jacobian of the times the Cauchy stress. Why do I want to times the Jacobian? Huh? Change of volume or change of area, okay? Or the change of line or whatever, okay? It depends on whether you talk about the tractions, individual component, or the volume. Then there's also another stress called first Pilokov stress. First Pilokov stress, which is actually also have a 2-point tensor F, one index in the current and one in the reference configurations, and is actually related to the Konikov stress, but actually times the F minus T. Okay, so why is that? Okay, why do I actually want, this time why do I want the minus T? So this is actually indirectly related to J tower dot F minus T. Okay, so let me give some hints. It's related to the Nelson formula. If I want to actually compute a force density or actually the total force in a given area in the current configuration, let's call it dF, then that would be actually equals to the normal stress of the Cauchy stress times delta dA, right? Does that make sense? Okay, and I want to have that relationship that actually equals to P dot N dA. Okay, I want the first particle stress to actually could be corresponding to be defined in a similar manner like the end in the reference configurations. Now the material is continually deforming. Okay, so in order to do that, I actually need to recall the fact that actually would before I reaching these conclusions. So what I actually want to do is that I want to write sigma equals to J F minus T N dA, which is actually just the Newton's formula. And then if I substitute it back here, these three things actually lead to the first particle stress. Okay, does that make sense? So as you can see here, sigma is symmetric. So the transpose of sigma ij actually equals to ji, or actually, or maybe I can write this. Sigma ij equals to sigma ji. Okay, and tower Ji, Ij equals to tower Ji, meaning that they're symmetric. Okay, how about P? Is it symmetric? It's not symmetric because F itself is not symmetric. Okay. However, it has a very nice property. P is actually the energy conjugate of the deformation tensor, while the other stress, Cauchy stress, is actually not directly corresponding to the deformation gradient. Okay. Now, the drawback is that P itself is not a symmetric tensor. So for convenience, people sometimes like to use the second Pilogov stress, second Pilogov stress, which is actually S equals to F minus 1 dot P, which is actually equals to F minus 1 dot tower dot F minus 1. Okay, and this one becomes symmetric again. Okay. Okay, so far so good. Now, what does that mean to write a constitutive law? Writing the constitutive law for large deformation is that either I'm giving you F history and then you try to write a P, that is one options, or I write the C as I give you a bunch of C and then you try to find out what is the S, the second Pilogov stress. Or I will give you some B tensor and then your goal is to try to find out what is tower. Or I will give you the rate of deformations and then you try to find what is tower. Now tower is not shear stress, but the canonical stress. Or in some case sigma, if you actually can get rid of the Jacobian. Get rid of the J, okay? So those are the options of writing the formula. Now, in small deformations, what we're trying to do in the analog is to giving the strain to find the stress. Okay. If this is a large deformation, this is actually finite deformations. Finite deformations basically meaning that I deform the material so much so that the reference configurations, the difference between the reference configuration and the final configurations can no longer be ignored. Okay. You see what I mean? That can be due to the deformations a lot, or I don't have that much deformation, but I have a lot of spin or rotations. That could also be the case. And then this is actually called small deformations or infinitesimal deformations. So what it means is that the deformation is so small, I can actually assuming that the reference and current configuration is actually pretty much the same. Okay, let's go back to the now, what actually happened is that here, okay, so I want to write model. So these arrows are the model that we try to write. Okay, now what is important is that which input I put in could have an impact on the model that I'm going to write. And I want to talk about what is the implications of the physical quantity that we talk about. Okay, and one is actually related to the spectral decompositions. Okay, how do I do the spectral decompositions of all those tensor? Now, this is actually very important is to know whether I have a symmetric tensor or non-symmetric tensor. Okay, now go back to the original work. What is something special about the symmetric tensor? Symmetric tensor have left and right eigenvector, but they are identical. Okay, so what happened to a non-symmetric tensor? Non-symmetric tensor have left and right eigenvector, but they are not identical. Okay, so what is the implication of that is that it will generate different level of complexity for the spectral decompositions. For the C tensor, that are the right Cauchy green tensor, the spectral decompositions give us these expressions. Okay, it's like the small deformation versions, except that now n is the reference normal. Okay, it's a normal vector in the reference on deformed configurations. Okay, so if in the analog, if I apply f equals to a, sorry, maybe I do this. Maybe I put a better example. If I do this, and then apply apply a force F, okay? And then after I apply the force, if let's say it becomes something like this, okay? Then I'm actually talking about these reference normal directions, not these normal directions, okay? You understand what I mean? Yeah, you understand what I mean? So because this is a deformed surface now, this is on deformed surface now. Before I apply the F, the force is the surface is vertical, so it's pointing to the up directions. Now after I apply the F, it's actually deformed. So then the actual current deformation is in the not necessary in the vertical direction in this particular example, right? Okay, so C is actually on the undeformed configurations. In the analog, what happened to B? B, on the other hand, as you can actually see, is also a symmetric tensor, but then the stretch would be in the current configurations. And then the stretch in the reference, delta A lambda, delta A, and then the delta A with the overline, they are actually with the tie on the top, they are not identical to each other. Where in general, dA is not necessary equal to this, okay? They are not necessarily identical. Now that begs the questions, what is the spectral decompositions of F? Okay, what is this? F, if I actually write it in spectral form, it would actually lead to lambda A. Now this is also a different lambda. And that would be equals to NA. Okay, does that make sense? Okay, so where is the rotation come from? The rotation, this one is itself is actually the rotation that do the polar decompositions. Can you all see it? Can you all see it? Okay, this is actually the rotations. A rotations can be formed by the tensor product of two normal vector. Does that make sense? Like sine, cosine, cosine, sine. Okay, why is that? Because the tensor product of that, the determinant is actually equal to 1, and then the transpose equal to the inverse. Okay, but if n and if the small n and big N are the eigenvector, but they are not normalized, then it will introduce deformations. Okay. So far, so good. Now, why do we care about this? We will actually find out later. This has been something. This has been something to do with this. Okay, in the spectral form, that we get a chance to connect the small deformation with the large deformation without changing so much about the formulations. By the way, what is the difference between delta lambda with nothing and delta lambda overhead and delta lambda tie? So delta A is called the principal stretch, and then this one is actually square of this. Okay, can you see that? Okay, because I guess you can kind of make sense to this when you actually record this. Okay, you see what I mean? So, and F can be decomposed into R and U. Now, as we have, this is actually with that. Then there is also another complications that are coming from the large deformation, but not so much for the small deformations. And this has been a major topic for a generation of continuum mechanics people with a lot of maybe quite a few of controversy topic that are generated of it, and there's a lot of fight on what is the definition of it. But here I just take the most simple explanations. Okay, the objectivity. What is the vocabulary objectivity mean? What does objective mean? Okay, my observation is very objective. So what does that mean? So objective in English writing mean free of bias, right? Or free of perceptions or whatever. Okay. What happened to mechanics is that objectivity is often related to film indifference or film invariance. In a computer science, there's a difference between film invariance and film equivariance, but here we won't talk about that. We simply use the mechanics definitions. Film invariance, okay? What does that mean is the following. If I have an object, B, undergoes some deformation, okay, and I describe it with some coordinate system, okay? Now I describe the same process, but with a new coordinate system, okay? What should happen to that process? Okay, by changing the coordination system, it should be identical, right? Okay, I'm just simply observing from a different angle. Okay, so you see what I mean? Okay, so if I, in the image classification analog in computer science, if I take a picture of George, for example, and then you identify him as a grid, and I rotate the picture 180 degree, he won't become Chinese or something, right? Okay, so that classification problem is invariant to the rotations. Okay, does that make sense? Okay, the same thing for the store of the energy or actually the stress. Okay, the stress would be considered equivariance, but here let's talk about the energy. If I compress the material in certain way and I rotate my observer, I should store the same amount of energy independent of the coordination system, right? Does that make sense? Now, how do I mathematically represent the difference between a coordination system? So let's say I have a coordinate system defined in different configurations. Okay, so how do I change the coordinate? Okay, which is actually, by the way, very important for say we want to simulate a wind turbine. Okay, so what happened to a wind turbine? How do I model the motions of wind turbine? Okay, there are two ways. One, you actually literally create a mapping for the rotations, which will work. Another way is that when I'm simulating the wind turbine, I actually fix the turbine. I just keep rotating my coordinate. Does that make sense? Right? I can actually predict the motions. I can actually express the motion in these two ways. Okay, so there's a lot of excitement in there. Okay, so how do I actually representing this? Okay, I can actually argue that the two coordinate systems that separate by something called rigid body rotations or rigid body motions. Okay, you understand what I mean? I have that XYZ, I have this XYZ. Okay, what is the relationship between the two? I should be able to introduce rigid body rotations to get the, rigid body rotation and translation to combine them. So a rigid body motions contains of two components, the rotation term and the translation term. You don't need to have that two term, but you can at most have these two type of rigid body motions, okay? So in this case, I would actually write a new coordinate system where the C is actually the rigid body translation and Q is actually the rotations. Okay, does that make sense? I will introduce another mapping that are actually mapping it into the X plus. Okay, what is that mapping did? It did nothing except I changed the way I actually want to write X and Y. Does that make sense? Okay, so Q is actually a rotation tensor. So Q belongs to special orthogonal group. Okay, and C is actually simply a vector of anything. Okay, Y doesn't matter what C is. C just need to be a real vector. Okay, it cannot be complex values. Okay, Y doesn't matter. It's not a function of X. Okay, this term is a linear function of X because there's an X term here. And this one is actually simply a function of time. So what it means is that I actually moving everything together, okay? So, and if something is material film indifferent, it means that it will be identical between these two configurations, okay? You understand what I mean? So there's a reference configuration here, and there's one current configurations, and then another configurations, which is actually also the current configuration, but I actually described it with a different coordinate system. Okay, so now in this case, if I look at the tangent, ft will be equal to q dot f. Okay, I just simply rotating the tensor. Okay, does that make sense? Okay, so let's see what happened for different constitutive model. Very important. So let's see. I actually want to write on the current configurations where there is no which is actually a free index. Okay, so this is actually what happened. What is the this is actually the free index that applied to the positions. The model in terms of C. Okay, I want to write a model that takes C as an input and output the energy that are stored by the deformations described by C. Okay, so this is one way of writing a model, and this is actually called hyperelasticity model. Okay, and now I'm assuming that if I take the deformation gradient, I can get back some of the some interesting measure. Maybe it would be some kind of stress. Okay, this is called hyper. Now, what happened to that model? Okay, so let's see. I want to check whether the model written like this is objective. So what I would actually want to do is to see. I simply change the observer of C, right? Does that make sense? Okay, so how do I do it? I will first describe the deformations, okay, from the reference B0 to B. Okay, now and then I'm going to introduce the rotations that actually do nothing but to change the perspective, okay, consecutively. Does that make sense? Okay, and then observe what is the energy here and what is the energy here. Does it change any energy? Okay, does it cause any energy to change the coordinate? If I actually change the amount of energy when I actually change the basis, that means it's not film indifference. There's a difference when I choose different film, right? Okay, so to do that is actually very simple. Let's see what happens when I actually choose to represent actually. And here, the deformation is C. Here is the C plus. Okay, and C plus is actually can be described as the F plus T dot F plus. Okay, does that make sense? And this one is actually equals to the QF T times QF. So far so good. Okay. So the transpose of QF is actually FT QT times QF. Okay, this is also good. This is actually equal to FTF. This is actually hence equal to C. Okay, so what is the lesson learned here? No matter what coordination system I choose, I would simply get back the same C. Okay, so it doesn't really matter. What coordinate system I pick, the C is identical, and hence the input. If I write the energy in terms of C, it won't be sensitive to whatever rigid body rotation I impose on the current configurations. Does that make sense? Okay, so this is actually the results why all the material model we write in C is actually material film indifference. Okay. Now there's another choice. Sometimes people want to write E, which is actually 1/2 C minus identity. Okay. So E is actually also another strength measure that the company use. Do you know why sometimes people want to write C? Use E instead of C? None, can you guess why?
When F is identity, E is a 0.
Yeah, exactly. Okay, this is just a renormalizing technique. If F is identity, there's no deformation, right? So if F is identity, then it implies C is identity. Okay, but this is not always convenience, because if I write the functions, then I would have to take identity matrix as the input and then output no energy. Then I don't have the homogeneity that make the model writing easier. So sometimes for convenience purpose, we use E to write a constitutive model, not for any specific reason, just to renormalizing it, in my opinion. Okay, just so that when E equal to 0, it implies C equals to identity, and it implies F equals to 1, and it implies no deformations. Okay, so you just get that homogeneity, a nice property, and this is whether you want it, it's just a matter of habit. I don't really think that this should be considered a religious issue. Okay. So now, this is actually one of the thinking that could be actually really useful. And there's also another part that could be important, is that there are also another options that we can actually see. Body rotations is actually up high. Now here is actually the isotropy. Okay, so how do I make the material actually, how do I actually make the material isotropic? Okay, what I mean is, what isotropy mean is that if I have a material that of some property, and then I actually load the material in these directions with the some amount of force, and I apply the material in this amount of the force, providing that the magnitude is identical, I will get the corresponding response that are actually equal to each other, that are equivalent to each other. Does that make sense? Okay, so for example, a stack of paper is not isotropic because if I actually, so let's say this is a notebook. If I shearing in these directions, I will get a different response than I shear in these directions. Okay, you see all the buckling. Okay, so this is actually an isotropic behavior. Isotropic behavior is actually something that doesn't depend on the directions. Now, this is actually in analog to the material film indifference, and it has something to do with the deformation tensor and also the nature of the mapping. To enforce isotropy of the material, I will consider the rigid body rotations on the reference configurations, and then I would introduce that rotations on X. Okay, You know the difference between what we did for the material film in this one and here? Previously, this is actually applied to the dummy index on the reference configurations. That means that I'm actually have a rigid body motions on the reference configurations, and if I do it, then as we show it before, if I define the deformation gradient this way, then the new configurations will actually give us the ft.qt. So sorry, t plus is equal to the t plus would be actually equals to f.qt. Okay, so if I do that, then actually what happened is that ct would be equal to ct dot ft, which is actually equals to qft dot fqt, which will be equals to q dot c dot qt. Okay, so you see here the q no longer actually taking out get cancelled out. Okay, what instead we get is something like a stress is like equivariance. You see what I mean? Do you see that? Okay, now what happened to the B? The B matrix, on the other hand, because it's actually defined like this, and what we have is that it will be equal to fqt dot q dot f equals to t equals to f dot ft equals to b. Oh, sorry. So if I change the material, if I change the directions of where I apply the force and consider the strength, I would actually get back the same B, okay? Regardless of where the material, which way the load is applied. So that actually implies isotropy. Okay, isotropy here mean not depend on directions of the loading, okay, or the change, okay. So so what it implies is that it would actually only equals to the. What it actually implies is that if I write the energy, okay, let's use this symbol as a functions of b, then I can also equivalently write it as a functions of the eigenvalues of the principal stretch. Okay, so they're equivalent. Why is that? So if one exists, the other one has to exist. The reason is the following. If I have a material that is isotropic, that means that I only care about how it low, the magnitude it low, the combination of the eigenvalue. I don't care about the eigenvector, right? Okay, if I don't care about the eigenvector, I don't need to put the eigenvector as a function. Okay, so I end up only put the eigenvalue into the input, and I can get back the energy that I got. Okay, so isotropy actually make it imply that I can write a model like this. Okay, you see what I mean? Which is actually in majority of the case we would like to write in the constitutive law. Okay, so far so good. Okay, so I know it's not easy, but okay, so that we can have everything that elastic. So what happened to plastic? Okay, I'm just talking about the deformation gradient. I never told you which part is elastic and plastic. Okay, so what happened to the plastic material behavior? Okay, what should we do? Okay. Now, in small deformations, we're saying that the total strain rate is actually equal to the elastic part strain rate plus the plastic part of the strain rate. Okay? Does that make sense? Okay, in large deformations where the configuration is keep changing, can we do that? Can we say F dot equals to Fe dot plus Fp dot? We can, okay? Why is that? Because you're describing that change of the configuration using a mapping, okay? And then you cannot necessarily add two things and make it work. Why is that? Because F itself is not an arbitrary a second order tensor that just provide you the mapping. Is the linearizations of the deformation mapping that, by the way, need to be positive definite in order to guarantee it to be one-to-one, right? Okay. So what happened to that kinematic is the following. We need to introduce a concept called that this is actually called the additive decompositions, meaning that the total strength can be split into the elastic part and plastic part using by using additive decompositions. Okay, literally. But in large deformation, what you need is multiplicative decompositions. What I mean is the following. I have a deformation gradient, and then I will split it into the elastic part and the plastic part. And notice that is always in this order in classical continuum mechanics. Okay, why is that? Okay, there's a physical implication to it. I would actually have a deformations, okay? I have a body that are undeformed, okay? Now I'm going to apply the total deformations to make it deform. Okay, now I change the shape. Okay, what is actually what is the multiplicative decomposition doing is that I assume I can actually first deform it in some way, okay, in the linear mapping Fp, so that it's actually deformed without changing the stress or energy. Okay, does that make sense? Then I would actually apply, let me doing this. This is not completely accurate. So this is actually the F. This is already the linearized mapping. Okay, I want to able to split it into two mappings so that I will have this intermediate mapping that actually only apply the deformation gradient, the plastic part of the deformation gradient, and then I apply the elastic part. So this part, these portions of it, give me the change of the stress. Okay, so stress is changing. Okay, what is interesting about this part is that stress is not changing. Okay, I assume that if I develop plastic deformations, I would actually able to find a way to mold the material into a new shape without changing the stress, so that I will have that configurations that I can actually now any other change on the configurations would now introduce stress. Okay, why is this thing exists? Why do I need to split it into two parts? It's because it's the definition of the plastic deformation, right? Okay, you understand what I'm saying? I actually permanently deform something. What does that mean is that if I remove the load, this thing won't go back to the original shape, right? So what does it imply if it doesn't go back to the original shape? Okay, it doesn't store any energy for that deformations anymore, right? Okay, otherwise, once I take out this, I will release the thing and then it should go back to the original shape. If I store the work done, I convert the work done into internal energy, and then if I take out the external force, it should get back to the original shape. Now it cannot, so that implies that I can actually have the FP exist. Okay, you see what I mean? So this is the tricky part. There's also a question about that because FP is never unique. You can apply rotation there and then you still get the same results. Okay, but practically, what do we want to do with that? How do we want to handle this? Okay, so we need to think about how do we want to write the constitutive law in order to able to handle that. Okay, you see what I mean? Okay, what do you think is the right strategy? Well, by the way, which one is easier? This one or this one? Okay, if I want to write a constitutive law that take f and then give me the p, this is already much harder. Now I have to deal with that multiplicative thing. So deal with this multiple thing is actually very hard, and I don't want to deal with it. Okay. I mean, I think if you are my PhD student, you know that I hate did anything difficult. I only want to do small and easy things. So I think. Okay, so what are the easy options? What are the easy options? Does anyone know? I want to do something. So the trick people think about and have been used for many times is that somehow I want to do the operation here. Okay, I want to able to do something very close to this, but I want to actually have the effect of this. Okay, the best of the two worlds. Okay, how do we do that? Huh? Yeah, logarithmic and exponential mapping. Okay, what is so important about, what is so interesting about exponential and logarithmic mapping? Okay, if I have a log, so what is the algebra of log A plus log B? What does that equal to? Or actually, let me look at this. If you have a, if you in your undergraduate course, if you draw something in a log scale, that are actually log A, and then this is actually Y or whatever. So if this is a straight line in the physical space, what does it look like? Yeah, it would look like this, right? Okay, so what is actually so interesting about what is the physical, when do you actually get an exponential operator? When you have A dot A dot A dot A dot A dot A dot A, you will eventually get an exponential operator, right? Okay, so that actually hopefully provides some intuitions on dealing with the large deformation mapping. Okay, so the trick is the following. I have this highly nonlinear problem, okay, and I want to actually somehow using the logarithmic way to actually simplify it. And there is a very important relationship to that. Is actually the relationships between the deformation gradient, the C, and then the epsilon. Okay, so the small deformations. In the literature, you would actually see two different type of research. One is actually relate the epsilon to the lecture log of C. Okay, so I apply the lecture log of the deformation gradient to get the epsilon, and then I use the epsilon to actually update it. Another way is to associate the epsilon with the log B, not B. Okay, the left Cauchy green tensor. So the first part is actually done by Coutinho and Ortiz. The second part is actually in the one of the textbook that we use on the B tensor. So which one is correct? Obviously, only one of them is correct. It depends on how you actually view the deformation gradient is actually performing. Okay, so let me, without further delay, let me talk a little bit about this. Okay, so in this case, we will actually use the textbook idea that we focus on the development of the constitutive law based on the left Cauchy green tensor. But keep in mind that it actually restricts it to isotropic material. So let's recall what happened to the waveform in small deformations. I would actually have sigma equal to C E double dot epsilon E equal to C E double dot epsilon minus epsilon P dot. Right? Does that make sense? And then epsilon E is actually equals to, in the predicted case, I will have this. Okay, I will assume everything is elastic, and then in the corrector, I would actually want to make sure that I would actually want to find out which portions of it is elastic, which part is actually plastic. Okay, so what happened to the finite deformations is the following. I will still have the waveform, but then instead I actually want to introduce a relationships. I will write first the energy as a function of the left Cauchy-Green tensor. Okay, so this is actually called the energy functional or the elastic store energy. Okay, so for the large deformations. And then I would actually relate that B with the conical stress, which is actually have this funny shape. If I take the derivative of the elastic portions of the B, I would actually times B dot, I will actually get the Cauchy, I will get the conical stress. Okay, now BE is actually equals to FE, FET. Okay, and I still have the F equals to the elastic part equals to the combination of the elastic speed and the plastic speed in a multiplicative manner. Okay. So now for each time step, I would actually consider, instead of epsilon dot, I would consider the B dot. Okay. I will have a predictor step that actually B dot E. Okay. Which is actually equals to L dot BE plus BE dot LT. Okay? Does that make sense? I'm just skip some step there. Okay? And in the corrector, I would also need to introduce new notations where the BE is actually the BE dot is actually the Lie derivative of the BE. Okay. So what would that be? I think that I need to introduce some detailed notations. So BE dot in the correction term is actually equals to L dot BE plus BE dot LT, the Lie derivative of the BE. And the Lie derivative of the BE dot E is actually equal to minus 2 lambda dot the gradient of the particle potential times BE. Okay, so this is equivalent to the in the small string level. In the infinitesimal string, I would definitely have that. I will only have that lambda dot this if I have the associative flow. If I have non-associative flow, I write it in G. But as you can see, in large deformations, I actually need to replacing this into this particular term. Okay. So how would that algorithm work? The algorithm will work in the following. I would actually using the spectral decompositions to decomposing the B into the spectral directions, and then I would actually leveraging the fact that in the spectral directions on the B and then the corresponding canonical stress which share the same basis, and I'll just update the eigenvalues of the stretch correlated with the corresponding with the eigenvalue of the corresponding stress measure, which is the canonical stress. Okay, so I'm just outlining it. But there is also another options to actually doing it, which I would like to talk in more details. Or maybe I should talk about the product rule first. I think I think I'm kind of running out of time, but let me maybe briefly talk about the other options that actually are quite equivalent and generate from this idea. Okay, so I write a return mapping algorithm that I actually want to do it in the following. In the small deformations, the stress integration algorithm is actually try to solve this problem. Given what is actually n plus 1, and given what is the new stress and the previous strain, and also the lambda, okay, try to find one of the following, epsilon p, okay, try to find one of the following, try to find what is the current elastic strain, or actually the stress, right, or what is the delta lambda, and also the delta lambda in between, right? Okay, now in the large definition versions, what you are given is actually the deformation mapping, okay, for the entire space-time, okay, but you are actually in the track of it like a roller coaster. You're at the middle of it, and then you are in some kind of intermediate configurations, okay, and then what you want to do is that from two configurations, configuration n to configuration n plus 1, can you find out what is the stress? Okay, do you know what I'm talking about? And then what I actually want to do is in between the two steps, I will linearizing the deformation mapping with f delta. Okay, so I have undeformed state, and then I map it in by some f, and then I'm in that configuration. What I actually want to do is I want to apply f delta, so that this is actually equal to f n plus 1. Okay, does that make sense? Okay, so this is also a little bit more involved than before. So how do we do that? We would actually say f delta, this is our approximations, is actually the identity matrix times the delta in the n time step times delta u. Okay, so what is delta u? Is just the relative displacement. Now this definition won't work if your deformations, if your displacement gradient is too large or the thing are very nonlinear. Then you will write that fn plus 1 is actually approximately equals to f delta fn plus 1. Fn. Does that make sense? Okay, do you know why fn is in the right hand side or on the left hand side? So it's the same thing. I apply the fn first, to which to I apply the fn is correct. So I first go to here, okay. So that gives you the fn portion, and then secondly I apply this to give me, so this whole thing give me fn plus 1. Okay. Now after that, what should I do? Okay, so what should I do? I can do something very smart. I can try to reuse the small deformation model by doing this. I would write bn e equals to the exponentials of 2 epsilon n e, and epsilon n e is simply the small deformations epsilon. Okay, you understand what I'm saying? Now, in order to get the b, in order to predict what is the new left Cauchy green tensor, I will create a drive stress there, and then I will assuming that between in these configurations, maybe I use the same color. Between these intermediate configurations and this configuration, everything is elastic. Okay, these are assumptions. Okay, to create a tri-stress state. Okay, does that make sense? So I would actually say everything is elastic, and then I write f delta bn e f delta t. Okay, do you know why I put the F in the left and right hand side? Do you know why Bn is in the middle? Do you know why? Because here, this is my new reference deformations. You see what I mean? Okay, or in other words, okay, how do I keep applying B for different time step? Okay, so let's say I have F1. I have a one deformations. Okay, the material go through one linear line deformation, and another one. I'll have first Ft, right? Okay, F1, right? The first deformations. And then if I want to apply another deformations, which is the composite of the first and another one, I'll write F2T, right? Okay, you see what I mean? So this is actually the original one, and I apply the F, and then I will get the new configuration, and I apply F2, and then it deform in another way, and etc, etc. And then the B is updating according to this rule. Okay, does that make sense? Okay, so this is actually coming up with like this. Okay, this explains why F delta is put on the left and right hand side, and in here I put a transpose here. So what happens if I want to do it for C? It will be identical except the transpose will be put on the left hand side, right? Okay, so now, long story short, let me talk about the next step. So what is the next step? I think then I apply the exponential mapping, right? Then I want to write something in a small deformation. So what do I need? Is I want to convert these expressions into epsilon n plus 1 e trial, okay? What is the corresponding thing between this and then the epsilon is the logarithmic mapping. Okay, I would actually compute, the next step would be to calculate this trial stress, and then I would get the log. I would apply the logarithmic part to actually convert this expression in the reverse order, okay? But now on the n plus 1 time, okay? So that would give me the lecture note of the BE n plus 1 trial, which I compute it here. Okay, does that make sense? Okay, this is very important. Do you all still with me here? Okay. So now what should I do next? I almost have everything ready. If the material is isotropic, maybe if I have an internal variable, I need to assuming that the internal variable are the same as the previous internal variable. And then what I need to do in the next step is to just apply it into the small deformation algorithm, because I already have this, right? I already have this, I have this, I have this, and then I also have the child of the stress right now. Then I applied it into the return mapping algorithm. So I would then use small deformation algorithm. And then after that, I just need to compute sigma n plus 1 equals to the determinant of fn plus 1 minus 1 times tau, and then that's it. Okay, so from that constituted law, I will get the canonical stress, and I apply the Jacobian. I can get back the Cauchy stress if I want to. Okay, so that's a trick. Okay, this is like magic. Eventually, I never deal with the complicated algebra of the multiplicative decompositions. I actually just use the small deformation theory, but I get the result of the large deformations simply using the logarithmic and exponential mapping. Okay, what is the limitation of that? Is that if you have a kinematic hardening or you have a loss of thing, internal variable that actually are rotating a lot, you need to consider that as well. This only work for isotropic case in general. Okay, does that make sense? I think we're running out of time. I think that there are people waiting outside, so I'll just stop here. And I think that